Welcome to a lesson on graphing the quadric surface, the elliptical cone. As discussed in previous videos, the degree and sign of the degree 2 terms, as well as which terms are present, help determine which of the 6 quadric surfaces is given. To graph a quadric surface, it's often helpful to graph the xy, xz, and yz traces, and these are where the surface intersects these three planes. To determine the xy trace, we'll set z equal to 0. To determine the xz trace, we'll set y equal to 0. And to determine the yz trace, we'll set x equal to 0. Sometimes when we determine a trace, it's just a point, but if we determine a trace that's parallel to the given plane, we can often find a better trace. Let's go and take a look at the equation of an elliptical cone. Here's the form the equation will take when the graph will be an elliptical cone. Notice it's equal to 0 instead of equal to 1, and all three degree 2 terms are present. However, two of the degree 2 terms are positive, and one of them is negative. Two of the traces will be hyperbolas, and one trace will be a point or an ellipse parallel to the third plane. And the axis will be parallel to the negative variable. Let's go and take a look at an example. Let's determine the three traces of this given quadric surface. Again, notice it does fit the form for an elliptical cone. So to determine the xy trace, we'll set z equal to 0. That's going to give us x squared over 16 plus y squared over 9 equals 0. Now the problem with this trace is the only solution to this equation would be when x is 0 and y is 0, and that would be a point at the origin. And that's not going to be extremely helpful as a trace. So what we're going to do is determine a trace that would be in a parallel plane. What I mean by that is if you take a look at this equation, if we let z equal 2, then we'd have 2 squared over 4, we'd have a minus 1 here. So if we add 1 to both sides of the equation, we could use x squared over 16 plus y squared over 9 equals 1 for our trace. Again, this would be when z is equal to 2. So this plane would be 2 units above the xy plane, but we're going to go ahead and use it as the xy trace. Again, this would be an ellipse where the major axis is horizontal and the minor axis is vertical. And the center is at the origin 0, 0. Here we have a squared equals 16, so a is 4. So we'll go 4 units to the right and 4 units to the left to determine the endpoints of the major axis, and then up and down 3 units to determine the endpoints of the minor axis. Again, remember this is not the exact xy trace, it's the z equals 2 trace, but it is parallel to the xy trace. To determine the xz trace, we'll set y equal to 0. So we'd have x squared over 16 plus, this would be 0, minus z squared over 4. I'm going to go ahead and move this to the right side of the equation, so we'll have equals z squared over 4. Now I'm going to go ahead and solve this equation for z squared by multiplying by 4 on both sides. That's going to give us z squared equals, this will be 1/4 x squared. Now we'll go ahead and take the square root of both sides of the equation. Both sides are perfect squares. We're going to have plus or minus 1/2 x is equal to z. Let's go ahead and write that up here. Again, we'll have plus or minus 1/2 x equals z. So this trace will end up being two lines, one with a slope of positive 1/2, another line with slope negative 1/2. They both pass through the origin. So for a slope of 1/2, remember this is scaled by 2, is we'll go up 1 and right 2. That's one line. And now we'll go down 1 and right 2 for the negative 1/2 slope. This would be the xz trace. Now let's take a look at the yz trace. It's going to be very similar to this. If we set x equal to 0, we're going to have y squared over 9 minus z squared over 4 equals 0. Again, we're going to go ahead and move the z squared term to the right side. So we'll have y squared over 9 equals z squared over 4. Multiply both sides by 4. We'll have z squared equals 4/9 y squared. Again, we'll take the square root of both sides of the equation. Let's go ahead and finish this up on top. We're going to have plus or minus 2/3 y is equal to z. So again, we'll let this equal the y-axis, this be the z-axis. So again, we have two lines passing through the origin, one with a slope of 2/3, another with a slope of negative 2/3. So from the origin, we'll go up 2 and right 3. There's one line. And then we'll go down 2 and right 3 for the other line. Again, these are the graphs of the surface when sliced by each of these planes. Remember, the true xy trace was a point at the origin, and this trace was z equals 2. If we take a look at the graph of this, you can see the three traces here. Two of them are two sets of lines. One of them is the green ellipse. If we take a look at a more dynamic graph using Maple, it would look like this. Again, if we take a look at this graph looking down on the xy plane, you can see the ellipse or the elliptical traces. If we take a look at the xz trace, you can see the two lines, which actually is a hyperbola. And if we take a look at the yz trace, again we have two lines which could be classified as a hyperbola. Here is our elliptical cone. That's going to do it for this video. I hope you found it helpful.